Okay, we've got a roller coaster car carrying a single child with a total mass of 100 kilograms. It's moving very slowly at point A at the top of the first hill of the track. The net force acting on the car parallel to the track is represented by F sub G. I think that's a G. I don't know. I can't see it. Let's make it bigger. Oh, F parallel. The strength of this force is shown by the graph below as a function of distance along the track, where the forward net force is positive. The only individual forces acting on the car are the weight force and the normal force, not friction. Okay? Note the various points along the track are labeled B through E. So we have point A, B, C, D, E along the bottom, and then our parallel component of force. Got it. Determine the net work on the roller coaster between position x equals 0 and position x equals 100. Yes. We have a graph. So let's first look at our y-axis and x-axis labels. We have force on the y, and then we have displacement on the x. So that means if we divide them, we have F over x. Okay. Spring constant? Nah, not useful. There's no mention of a spring here. So let's not use the slope. What else can we do? We can look at a point. Okay, not useful. What if we multiply the two? Oh. Doesn't that work? If we multiply the two. And if we multiply, that's the same thing as saying length times width. Right? So this means take the area under the curve, the area under a force versus displacement time, force versus displacement graph is work. Determine the net work done on the roller coaster between 0 and 100. So here. So all we're doing is getting our area here and getting our area here, adding them up and moving on our way. So we can just get the area of this, which will be 1/2 base times height, plus 1/2 base times height. You may draw the rectangle if that's your thing. Go for it. I don't care for it because I didn't learn it that way. I just don't. So half the base times the height, 50 times 400 is going to be 20,000. Divide that by 2, so that's going to be 10,000 here. And then this is the same triangle, so 10,000 here. So the total is 20,000. Remembering that work is area under the curve for force versus displacement. Is the net work found in part A due to normal force only, the weight force only, or do both forces do some work? Sorry. So if you think about what's happening, you have a car moving along a track in this direction, right? The force is acting. We have the normal force going up, and then we have gravity going down. It's a roller coaster. So no matter what, even if we're on one of these curves right here, our normal force is this way while our displacement is downwards. That means normal force is always perpendicular. Because normal force is perpendicular to displacement, normal force does no work. Ever. For this situation. Normal force does no work. So that means it's all due to Fg. The weight force. Does the car move uphill, downhill as it travels from 100 to 200? So now we're looking at the second segment of the graph. No. From 0 to 100. I skipped a question. From 0 to 100, what is the change in height for the car? Explain your reasoning. The work that we found earlier was positive, right? Not negative. So work is positive. And the only force acting is force of gravity. Fg does the work. For positive work, you have to have your force and your displacement, let's pretend like I can spell, in the same direction. So that means it has to be going downhill, right? It can't be going uphill. If it's going uphill, then the force of gravity is acting downward. Meanwhile, your displacement is upward. What about from 100 to 200? What is the change in height for the car? Explain your reasoning. All right, so let's first figure out how much work is being done here. So we have this triangle and that triangle, both right triangles. So we can say 50, and then the height is 200. 50 times 200 is going to be negative 10,000, and then negative 10,000. So we have negative 20,000 joules of energy. So based on our explanation for the previous one, we know we're going uphill because gravity is in opposite direction of displacement, or the angle between the two is 180 degrees. We'll just put a period, right? I think there's more to this question, isn't there? Now, draw the roller coaster track to the right, assuming that point C is the lowest point on the track. Label all 5 points on the track. Let me expand. So we know that point C is the lowest point on the track. So that means, whoop, let me get my pen back. Point C is about halfway through. There's our point C right there. Point A is up at the top. And point D, E, is also going to be up at the top. We know that point B went 50 meters, looking at that graph. So to figure out where point B went, we're going to use UG equals M, mass of the thing was 100, times G times 10 times H. Whatever H is, that's what we're going to be able to figure out here. So for the part from A to B, how much work was done? 10,000 joules. All of that was equal to this gravitational potential energy. So it's 10,000 equals 100 times 10, which is 1,000, times H divided by here. H equals 10 meters. B. There's point B. And then point D, somewhere over here. I believe our work is the same for point D. Yep. Well, this time in negative 10,000 joules. So it's going to be negative 10,000. Same mass, same G, divided by 1,000. Our H is going to be equal to 10. Well, 10 again. So point D goes here. The energy bar charts for here, at the top, we have all gravitational potential energy, and we have 10,000 joules here. And then for point B, we're half and half, so it's 5,000 and 5,000. And then point C, we have no gravitational potential energy because we're all the way at the bottom, so all of it is kinetic energy. Point D, again, we're half and half. Point E, it's all gravitational potential energy. Oh, I think it's got to be 20,000 joules, right? That's what we said earlier. Sorry, trying to rush, short on time.